Hello, this is Aiden Bunting, and I'm working on Project 2 of Fluid Mechanics, and I am assigned Part C for this, which is finding the wall shear stress and the skin friction coefficient. So for this one, I'll walk through how to set it up, but it's basically the same as Part A and Part B. So first, you're going to want to go into your geometry. So once you open it, it'll look something similar to this. I just made a flat plate 100 centimeters long and then 20 centimeters wide. So, and that's based off of the dimensions that you're given in your project. So once you do that, you're going to want to go to concept and make sure that you just surface from sketches. So that's what you're going to do in sketches. And then next, you can move on to your mesh. I'll quickly run through the mesh as well. So for this mesh, you're going to want to create 3 different edge sizes. Your first one is going to be between the top and the bottom of your plate. The second one should be your inlet, so the left side. And then your right should be, or your third one should be the right side, so your outlet. And is how your setting should be. Um, just make sure it matches these for your first one between the top and the bottom. For your inlet, you're going to want to have it pretty much almost the same, except some stuff down here in the advanced section has changed. Just make sure your bias type is the first one. It looks kind of weird, but I don't know why it's like that, but just make sure you have it as the top bias type for your third, and for your third edge size, which is the outlet. It's the same as the second one, except you're going to have a reverse bias, which is just you're going to select the outlet as your edge, and then you're also going to make a face mesh just on the front face, matching these settings right here. So once you did all those, you can name each section. I named the top one symmetry, I named the bottom one plate, and then the left inlet, the right outlet, and then just the whole thing airflow. And then so once you do this, you can generate your mesh by going to mesh and then just generate. And then it should look something like this, where it's the squares on the top are kind of big and then they get smaller as you go closer to the plate. And the reason why they have to be smaller down here is just this is where your boundary layer is. So the mesh has to be very fine down here. And that's pretty much it for the mesh. And so now that you're here, you're going to have to run your residuals, which is what you're going to be doing in part A and part B. So I'll run through how to do that really quickly as well. So you're going to go to models, just make sure it's set on laminar because you want laminar flow. Go to your materials, make sure all of this looks right based on the given values that you have for your project. So these were mine, so I changed them to these. Next, you want to go to your boundary conditions. Make sure your inlet has a velocity of 2, again, which is given in the project description. And then for your outlet, just make sure you turn on prevent reverse flow, and these values match. Should apply and close. And then next, you can go to your reference values and just make sure that everything looks right based on your project description. And then you can also hit compute from inlet because your flow is going to enter in through the inlet. So just make sure you start from your inlet. And then so next, after you do that, you can initialize everything. You can compute from the plate, and then just make sure it's your x velocity because that's the direction your flow is moving in. And yeah, after you do this, you can hit initialize, and then you can run your calculation. It's going to look something like this. After you run your calculation, you can move on to actually plotting the wall shear stress and then the skin friction coefficient. I'll show you how to do it from the beginning. So you're going to scroll down here to results and then hit plots. Oh, and then just hit XY plot. And then so now that you're here, you're going to change your y-axis function to wall fluxes. It should default to wall shear stress, but we're going to have to find the wall shear stress and the skin friction coefficient. So we can just start out with the wall shear stress. So just make sure your velocity is going in the x direction, because that's where our flow is flowing, in that direction. And then your surface is going to be your plate. And then so once you have all of these selected, you can hit save and plot. And then this is going to be your your ANSYS graph, because we're going to have to compare our ANSYS values and our theoretical values in Excel. So this is just what your ANSYS value is going to look like once you graph it. And then in order to get this information over to Excel, you're going to want to hit write to file, write, and then you can select somewhere on your computer to write your files, and then you just open that file with Excel. So that's the wall shear stress one. So let's do this again. So you're going to hit this again to do the skin friction coefficient. So again, you're just going to hit wall fluxes. It's pretty much the same exact setup. Change this to skin friction coefficient. Again, just make sure it's in the X direction. Hit plate again. Hit save and plot, and it will look something like this, your skin friction coefficient. So just make sure it looks something similar to mine, and make sure you write the files to a location where you can easily open it. And so now we will look at the data in Excel. Okay, so now once you import the data into Excel and you open up the data with Excel, it'll kind of look something like this. You'll get these two columns right here. These are just the plate distance, so the X values, and then these are going to be your wall shear stress values for this one. And then I calculated the theoretical data as well in Excel in order to make a chart, which you are going to need to do for the comparison in this project. And then also I did the same for the skin friction coefficient. Again, once you import it into Excel, it's going to look the exact same as this. And then I calculated the theoretical values right here in order to make the chart. So yeah, thanks.